you do it in the neutral state, or do you want me to add?
Okay, so what you would do is for the cadmium ion, if you're just pulling off of that,
it goes from any ion. I mean, it goes for any ion.
It goes for any ion. So,
yeah.
So the setup there would be if I have cadmium has a configuration of krypton. Yeah. So the atom itself would be krypton 5s2.
We can write it in the short state.
Well, it's asking for noble gas, so that is the short state.
Okay, because I remember it was saying full state on the, might have been on the quiz or the.
Well, on the quiz, one of the questions asked for full configuration. One of them asked for noble gas.
Okay, well, yep, I probably, yeah. And on that, I put spaces in between, and I can't, like, well, you did say put parentheses around it, but I was trying to raise it. It's supposed to be
superscript, but you know, I've talked with a couple of you about this, and some of you have trouble getting that text editor to work. So if you do it like this, that's fine. That's fine.
Okay, because
we've established that as far as we're concerned, parentheses mean the same thing as superscript. So if you did it this way, that's fine. Now on the exam tomorrow, you're going to be, you're probably going to be handwriting everything. So,
okay.
You know, that part won't matter. Okay. But that's the configuration for cadmium atom. Now for cadmium ion, what does that 2 in parentheses mean?
That is plus, it's plus 2.
It's plus 2, okay? So, so should I add 2 electrons to the end, or do I need to take 2 electrons away?
You got to take them away, and that's,
okay.
Yeah.
Okay, which electrons are we taking away? So it's still krypton.
The S2.
Yeah. Yeah, so
5s.
So 5s2, we're taking away 2 electrons. So those 2 electrons go away. That's 5s0 now. 4d10. So you could set it up like that. But since this one's empty now, we could also write it as krypton 4d10 as well.
Okay, so you do, okay, I was right. You do go ahead and take it out. Take it out.
You can.
When it says +1 or +2. I mean, +1 or -1. You add it or take it away. Add it or take it away. Okay, that's correct. Let's see what else I need. Let me see. Oh, that quantum number.
Okay.
Okay, when I look at, okay, so you just got to answer if it's a possible set or not.
Yeah, that's all that this is. So this is a lot like the example we did in class.
Yeah. It has to do if it's in the certain orbital. Yes.
Yeah. So we look at each of these and we go, is this combination possible? And so,
And if it is, just put yes.
well, what it's asking is for us to strike out the ones that are not. So if it is a good set, then we just leave it alone. If it's not, then we cross it out.
Okay, that's fine. That's fine on that one. And then I know empirical formula. I know that. I just gotta look over a couple things, and then are we gonna have a periodic table?
Yes.
Oh, okay. Because I was about to use. Okay.
Yes. So tomorrow, what you'll do is you will go into the part of Blackboard that's called exams. Mm-hmm. And in that, you'll see exam 1, take home exam. And there will be a downloadable exam as well as a periodic table and your equation sheet. Those will be the things that you're allowed to have.
Okay.
And then what you'll be responsible for is if you can print out the exam and write directly on the exam, great. If you don't have access to a printer, that's fine too. All you need to do is basically make yourself an answer sheet or answer sheets, and you just write out your answers on that sheet and upload it to Gradescope.
Okay. Okay. Okay, let me go over this. Okay, so looking at that element, atomic number, mass number, number of protons, number of neutrons. Okay, so look, I'm looking at it because I'm trying to remember more. So anyway, looking at it, the atomic number is that mass number. Like, okay, for example, the hydrogen is 1 point whatever. That would be the atomic number?
No.
That's the mass number, I know for sure.
No.
But I get it. No?
If you're looking at a periodic table and you're looking at a number with decimal points and decimal places on it, that is its average atomic mass. Its average atomic mass is not its mass number. It is not its atomic number.
Okay, that's where I'm getting confused. Yep. Mm-hmm. Well, yes.
So if you want to look at a periodic table, I've got one here. The number that you see, that is the atomic number of that particular element. So if I'm looking at, iron here, iron has an atomic number of 26. Thallium has an atomic number of 81. And that is the number of protons in its nucleus. So that's the information that we get from the periodic table.
Okay, the mass number is the two numbers calculated together. Because I'm looking.
It's the protons and the neutrons. You're right.
Okay, because I'm looking at the screen, your screen, and then I'm looking at this, and I'm trying to think. Because as soon as you said, because some stuff I remember, and some stuff just need brushed up on. Okay, that's fine. Then the number of electrons is the left, like 112 minus 76.
No. To figure out the number of electrons, you have to look at the charge on the species. Because remember, charge is equal to protons minus electrons. So if it's neutral, then the number of protons and the number of electrons is the same.
Okay.
If it's not neutral, then you have to look at how is it different. And so if I look at a hafnium here, I've got a positive 4 charge, and I've got 72 protons.
Yeah, you were -4.
And so you're right. The number of electrons there would have to be 68 to account for that difference.
Okay.
Just go down the stairs quickly.
Let me.
Just play in the water for a little
Let's
bit.
see. Test. Let me see. Okay, charge.
The ball's right here, silly.
Atomic.
There's the ball.
Mass number. Number is. Mass number is the mass number.
All right, boys, turn on the water and run around in the water for a little bit.
Let's see.
Play water.
Electrons.
Just walk down.
Electrons.
3, 2, 1, go. Just walk down quickly. No, you don't. 3, 2, 1, go. Just walk quickly. Go quickly.
I got that.
Good, Isaac.
Okay, the mass number was the decimal number?
No, you're thinking of atomic mass. Mass number is protons plus neutrons. Protons plus neutrons equals mass number. So I should be able to add those two together
Get the water out. Turn on the hose.
to get the mass number.
Okay. Okay, mass number, protons and neutrons, atomic number, number at the top. Okay, proton. Okay, I got that down. Are we gonna use the? I mean, are we gonna have the configuration table like for the feet to?
Yes, the conversions table is on that equation sheet.
Okay.
Now, you won't be given any metric conversions. It'll just be those English to metric, how many feet are in a centimeter, that kind of thing.
Okay. That's why H with the I have to look back for that one. I got that down. Okay, that first one, the volume of an irregularly shaped silver colored metal.
Okay.
The metal's density. Oh, okay. When it says determine the metal's densities, that's the D equals M over V.
Yes.
Okay, report
Yes.
change. Mass, volume. Okay, with the mass, the volume, mass, volume.
So you have to use the difference in the volumes. So this one is reading. This one's reading about 3.9 milliliters. And this one's reading about 5.40 milliliters. So the volume is the difference between the two. And then density would be mass over volume. So
We have to determine the metal's density. Okay.
So you take 15.2 grams and divide it by 1.50 milliliters.
See, this is that one where I told you that I was told like in a problem, they have to give you something. So they gave you 15.2 grams. That's what I'm used to. Yeah. That's, yeah, I've told that a long time ago. Okay. That's cool. I think. Calculate the following: the number of molecules. Yes. And determine the wavelength of light. Turn from N4 to N2. Okay, when they said determine the wavelength of light associated with the transition of an electron from N4 to N2, is that
Yes, that'd be the Rydberg equation.
yes, okay.
So yeah, you would set that up.
That's fine. Yeah, because I remember how we did it.
Yeah, 1 over wavelength is equal to RH times 1 over N1 squared.
N1 initial and F. Yeah.
Yeah.
Which has a smaller radius? AR. So radius. Potential useful. Okay, so you do give the, it says potential useful equation constants. You do give the formula.
Yeah. So you'll get this same sheet. You'll get this same sheet. That's going to be among the materials that you're given. And so, yes, this table will be in there. These equations will be in there. Not all of them will be useful, but you'll have access to all of them. So, little things. You don't need to know you don't need to know the formula for converting between Celsius and Fahrenheit. You don't need to memorize the values of the constants here. They're all given to you.
Okay, this is the one I think I got hung up on. I didn't hear what you said. It says an unknown molecule X is studied using mass spectroscopy techniques. Yeah. Atomic X is known to have 3 isotopes with the following abundance data. Okay, I got confused on this because I kept coming up on the same element as being the X.
Yeah. I was meaning to ask you about this because you made the same mistake on the quiz that you're talking about right here. All 3 of these are describing the same atom. All 3 of these are describing the same atom. It's just 3 different isotopes of the same atom. So you should get the same result for each of them. What you need to do is you need to do that weighted average that we did in class. Multiply the mass by the abundance. And then add together those 3 abundances and divide by 100 to get rid of the percent. And that will give you the average atomic mass of X, which in turn would give you the identity of X once you compared it to the periodic table.
So the mass times the abundance divided by 100.
So you would do this for all 3 of the isotopes, add them all together, and then divide by the 100 to get rid of the percents. Because otherwise, if you don't do that, then the answer here is going to end up being like 15,000.
Okay.
Which doesn't make any sense.
So you don't want them individually?
No, it's collective. You're going to put them all together.
Okay. Then when you get so you determine the average molecular mass of so then that'll give you the average, and then it says what is X. That's the element, right?
Yeah. Yeah, so compare your average mass to the elements on the periodic table and pick the one that's closest.
Okay. And that's the on the period that was okay. That's like the 1 point whatever for hydrogen, right?
Yeah.
That's what I'm comparing it to. Okay.
Yeah. Yeah.
Let me see.
Yeah, and so this technique, this is how we got those numbers on the periodic table. You take the isotopes that are possible for the element, you multiply those isotopic masses by their abundance, and you add them all together. And that gives you the average mass of whatever element that is.
Okay, I got that stored. I got that one stored. Let's see. I got that one stored. Okay, when it says classify each of the following as an element, compound, solution, or heterogeneous mixture, it's one or the other, or it could be multiple.
So it's not a matching question in that only one lines up with one. So these could be, you could choose any of these for any of them.
Okay, so it could be an element in a heterogeneous mixture.
Well, no. Each one of them is going to be one of those things, but you can use the multiple answers multiple times. So arsenic is only going to be an element.
Yeah.
There's no other classification for it.
Okay.
It's not really possible to be a compound and a solution. It's going to be one or the other. It's either a pure substance or it's not a pure substance.
Okay. Okay, I got that. Okay, convert the following. Okay, I got that one. You said look at it's a conversion. I got the ion one. Okay, they're all ions. Write the name in the formula. Okay, when it says write the name in the formula, okay, for the ammonium ion, that is the name, so you just write the formula, right?
Yes, so it's one or the other. So three of them I gave you the name, you give me the formula. Okay. 3 of them I've given you the formula, you give me the name.
Okay, that's fine. And then let me see, I got that one. Okay, when it talks about the number of molecules of CO2 in 1.17 mole sample, okay, that's that one where you do the mole conversion, the mole, the mass to get the molecules. That's the
that's where we use that chart in chapter 2.
I want to say so bad. I don't like to be embarrassed, but Avogadro's number? No?
I'm sorry? Yeah, Avogadro's number.
Okay, I was right. Okay, because that just kept popping up in my head to say. And sometimes I'd be scared to say something because I'd be scared that it's wrong. Like I know I have to convert to get the.
Yeah. So remember we had this slide.
Yeah.
So all of those calculations fit into this kind of mold, where in our particular case in this problem, we were asked to go molecules from moles of the substance
To molecule, yeah.
So we had moles of the compound. We wanted to go to molecules of the compound. It's all that's a one-step conversion right here.
Right.
Others in this set, let's see, grams of nitrogen for moles of N2O5.
It'll be mass.
So I had this. I start here. I have to go to here and then to mass. So that'd be a two-step conversion. And then the last one, atoms of carbon from grams of molecule That one's going to be the most complicated. I have massive compound. I need to turn into moles. I need to turn moles of compound and moles of element and then into atom. So that's a 3-step conversion.
Okay. Look at chart. Look at chart. The compounds consist determine. Okay, the empirical one. I got that one. I got that one. Determine the molecular formula of the compound. I got that because that's in with the empirical slides. The Bohr model utilizes energy quantization to explain phenomena of the spectra, define energy in terms of Bohr model of the atom, and explain how the model was to explain why specific line spectra exists for each element. Okay, that's that one where we talked about that Bohr model utilizes energy quantization to explain phenomena. That's that one where you helped me with if energy is going out or energy is coming in.
Yeah.
That's that one.
Yeah. So you've got your nucleus. You've got your energy levels.
Yeah.
And
you just got to explain.
They'd be full rings. But you know what we know is that each one of these rings has a set energy to them.
Right.
So 2, 3, 4, whatever it is. And so that's what quantization is. Quantization says that the electrons have to exist out on these energy levels, and these energy levels have set energies. And if an electron wants to go from one spot to another, there's a set amount of energy that would take. And that set amount of energy exists in the form of the line spectrum. So this particular gap of energy represents one line on the line spectrum. And a different energy gap would represent a different energy and a different line on the spectrum. And so, since that's the case, we're not going to see a continuous spectrum for any element. We're going to see a series of lines based upon how many different transitions are going to take place and what the energies of those transitions are. And obviously not all the lines are going to be blue. I'm just being kind of lazy here and not changing up my colors.
No, that's fine.
But what we would see is that individual elements are going to have different line spectra because their energy gaps between the energy levels are going to be slightly different from each other. So what we see here for hydrogen might be completely different for sodium. But the quantization comes from the fact that these energy levels have set specific energies.
Okay, because I do hear what you're saying because I don't want to get confused. Okay, when I just took my quiz, I explained that. That's the same question, wasn't it?
There was a very similar question.
Okay, so on my question, I explained it, but I don't know if I explained it right. Did you?
I haven't gotten to the, I was going to get to those after the review session.
Okay.
So
I want to see if I explained it right. I said that the amount because it was like, why do we, on the lines of why do we have those energy?
Well,
Oh, why can it only hold so much energy or something like that before it transfers? And I said that I just can't remember the question, but I remember me saying that it has to satisfy that energy levels.
Yeah, you got the question. Explain why an element will only absorb or emit specific wavelengths of light.
Yeah. And it has to satisfy that energy levels amount of absorbance before it can move on to the next level. And then that's where quantum comes in, because you can, and then the wavelength is formed, because you can't do it unless the energy is satisfied within that energy level.
Right.
Like you can't move on to the next. A wavelength is not going to occur, or quantum is not going to occur unless that energy level is satisfied with the.
Right. You can't make a transition unless you have the exact amount of energy necessary to make the transition.
Yes.
So if you're going up in energy, if you're absorbing energy to go up an energy level, you have to absorb the exact amount of energy to go from that lower level to that higher level. You can't go anywhere in between. There is no in between. And that's really what quantization is. Quantization says that there is no in between. There's here and there's here.
Yeah.
And if the electron wants to move, it has to absorb enough energy to make that transition. It can't go anywhere in between. And Bohr's model kind of perfects that and takes that to the next level by saying, well, that quantization is the reason why we have atomic spectra. And the way that the spectra look is because of the fact that there are no between energy states.
Okay, so define energy quantization in terms of Bohr's model of the atom, and explain how this model was able to explain why specific line spectrum exists for each element. Define energy quantization. Okay. So tell what energy quantization is, then just explain how Bohr's model demonstrates.
Yeah, how did the Bohr model use quantization to explain the phenomena of line spectrum?
Okay. I got that down. Okay. Yeah, well then that's okay. Which has the smaller radius? Argon or chlorine. Okay, what the radius is going by position.
Okay, so think about what we were talking about yesterday in office hour. I drew you those pictures. We used the Bohr model again to try to explain it. In argon and chlorine, you've got electrons that are both in the third energy level.
Oh yeah. Okay, I do.
Okay, so
which one is further away from the nucleus? Yeah.
Okay, so in the case of argon and chlorine, they're both in the third period. So their electrons are both on this energy level. So it's not a matter of energy levels in this case. It's a matter of what's in that nucleus. The more protons in that nucleus, the more attraction we're going to draw to those electrons and pull in those energy levels. So which one has more attractiveness, more pull in its nucleus, the argon or the chlorine?
Argon.
The argon. So argon has the smaller radius, and we can describe the reasoning as argon has more protons in the nucleus
Then chlorine.
and that's really all that we would have to say about this.
So let me ask you this. So the smaller the radius, the more the wait a minute. The smaller radius is the smaller radius has enough pull, has the more, so the more pull I have, the smaller radius I will have. The more pull, the more, okay, let me rephrase. The more protons I have.
If we are comparing in the same energy level. So if we're comparing atoms that have the same number of energy levels, then it's going to be the pull of the nucleus that makes the difference.
Okay, but if I have boron and chlorine, it will be boron because it's more closer to the nucleus.
Right. So let's take these guys off here.
Well, I understand it. I understand when you say the same, because they're in the same row.
They're in the same energy level. But if I'm comparing these green electrons to these purple electrons,
it will be the green electrons that has the smaller radius.
Right. Because even though there are more protons in the nucleus for the purple atom, the energy levels are far enough away that the purple electrons aren't going to feel them nearly as much.
Okay.
That adding that extra energy level, it's a phenomenon called shielding. The more electrons that you kind of put in the way, the less the electrons that are far away feel that nucleus.
Okay.
So if we're comparing inside the same shell, if we're comparing inside the same energy level, then the nucleus is what makes the difference. But if we're comparing different energy levels, then it's going to be the energy level that ultimately makes the difference.
Okay. Got it. And I wanted to leave some so that I can do it on my own and kind of make sure it sticks. So I'm going off by piece memory right now. Pieces of memory. So this is fine. So yeah, it's not. It touches on the what we went over, like to a T. So it touches over.
I mean, this is a comprehensive exam of the first 3 chapters.
Okay,
so
yeah,
you're gonna see little bits of everything. Now, this exam's probably a bit on the long side, but I wanted to kind of give you an example of all the different types of questions that could be asked. It probably won't be this long tomorrow, but these are all the things that you would want to know going in so that you can do well. And if you can do all of these things and you can do them well, you should do pretty well tomorrow.
Okay, yeah. Yep. So, yep, this is fine. And then I will get my calculations together on my charts and write it out on paper. Now that I have to upload it by hand because I wasn't able to print it off and scan it in.
Okay.
I might have to do it by hand. That's if I don't go. I might go get a thing of ink, but I don't know. That's if I don't go get a thing of ink.
It's fine either way. I've had students that have made just taken notebook paper and made their own answer sheets and submitted it that way. And it's fine. Just, make sure that when you upload it to Gradescope, you tell me where the questions are so that I don't have to dig for them. That's really all it is.
Okay.
But
Okay,
I mean,
that's fine.
if you there's going to be a multiple choice section. If you just want to number it down 1 to whatever and just write in your answers that way, that's fine. I can work with that. And that's actually one of the beauty parts of Gradescope, is that it does allow for some of that flexibility. You don't have to submit the exact form that I put on Blackboard to make it work.
Okay. Okay, yep. This works. This works. And I will be in the lab, be in the session tomorrow, because I haven't looked at that other lab. I looked at it and then it's like calculations and like a lot of graphs. So I'm gonna probably just, if I come across my calculations, because I know it has to be turned in tomorrow. So I will get to that when I come back after.
All right.
So yeah, I will be in the lab tomorrow. But yes, thank you so much.
All right, you're welcome.
Thank you.